Okay, Assalamualaikum and good morning. Welcome to our lecture session. Okay, so we still in chapter 2. Okay, last week we go for the topic with the single degree of freedoms for the free vibration. Okay, so for undamped system, so which is undamped system, so meaning that the system only consists of spring and spring mass system lah. So there's no damper. So damper we go for the next chapter. Okay, so last week we go for the free vibrations, and now we go for the second part for the chapter 2. Okay, so uh, the part 2, we go in detail more on the force vibration lah for the single degree of freedom, which is how we develop the equation of motion and analyze the response is due to the force vibrations. Okay, for the uh, if we draw the free body diagram for the single degree of freedom with the uh, excitation force, okay, so which is um, the force induced the system we represent as a F in the function of T lah. Okay, so F can be any kind of force. It can be the step function, the constant force, or the most common topic in this subject, which is the harmonic excitation. Okay, so harmonic, which is the force will be in the function of sine or cos. Okay, so in the free body diagram, where the force, we consider that the force were induced in the positive direction, in downward directions, and then um, the reaction force, the mass we move in the direction to downwards, which is the same direction with the force applied, and then the reaction force is come from the spring and the stiff the inertia to balance the system lah. Okay, and then for this system, when it goes to downward directions, the spring is in the compression mode. Okay, so which is the magnitude is kx, depend on the displacement of x, how much of x, the motion of x. And the inertia we goes to the opposite directions to the motion. Okay, so motion goes to downward, and the inertia we goes to the upward. Okay, so we summation for the reaction force come from the inertia and also the stiffness, and then came at the balance equation. Okay, then this is the equation of motion. Okay, now we go for the reaction. Okay, so the response for the single degree of freedom force vibration, actually we can divide it by two kind of response. Okay, so the first response we call as a homogeneous response or transient response. This one is the response is due to the initial conditions. Okay, so initial condition we have learned last week class. So when there is initial condition, you give an initial displacement or initial velocity, and then the system will oscillate based on its own natural frequency lah, the frequency. So this one actually the example for the damped system actually, because that's why we call transient. So meaning that it have a decay in terms of amplitude. But for the undamped system, actually the homogeneous still remain oscillate with the same amplitude without any decay lah. Okay, then there is a particular solution, or we can call as a steady state solutions. Okay, so this one is a the response is come from the induced force to the system. Okay, So for example, you induce the harmonic excitation force. This one is commonly applied as in the mechanical structure. So there is a lot of sources that can induce the harmonic forces, especially for the rotating machineries lah. So any motor or any reciprocating system. So either the engines and the rotating, all those kind of machinery, we produce the harmonic excitation based on the operating speed and also the component inside uh, that system lah. Okay, so there is two kind of motion with different frequency. Okay, so the homogeneous is depend on the initial condition. Okay, what is the initial displacement, what is initial velocity? The amplitude is depend on the initial conditions, but the frequency is depend on the natural frequency. So it will oscillate based on its natural frequency lah. And then there is a particular or steady state solution. Particular or steady state solution, which is the response is due to the applied force. Okay, so here the difference is for the homogeneous, the frequency is based on is refer to the natural frequency. Okay, which is dominated by stiffness and the mass of the system. But for the particular, it's depend on the excitation frequency. Okay, so if you have a motor, the motor running at the 10 hertz of the speed excitation, and then the particular solution also have the same speed, so which is 10 hertz lah. So it's depend on the excitation frequency. Okay, and then the amplitude is depend on the system itself lah. So this one we go detail after this. Okay, and then the combination of both of the uh, solution, which is we can call as a total solution lah. Okay, so which is combination of homogeneous and particular solution. Okay, so actually this happen especially when you try to start the engines or your car in early mornings. The first place when you start the engine, you found that um, have the higher vibration, right? So that's because it's at the beginning the vibration is combination of homogeneous and steady state. Okay, the homogeneous is a transient, so which is have a damping after a certain period of time, then it will diminish lah from in the total response. So which is after that is dominated by the steady state solution or particular solution lah. So that's the example lah, the total response. But this one for the damped vibration, for the undamped actually is keep just summation. But in actual application, there is not much example that can represent the undamped system lah, because even the spring itself have their own damping elements lah. So but mathematically we go in that condition lah for the undamped system. So just imagine that the summation of two sinusoidal wave with different frequency and also different amplitude as well. Okay, so basically in this subject we are looking at the kind of force we consider as a harmonic force. Okay, so harmonic, which is we can represent at the sine or cos function. Okay, so because this one it have more effect lah. So because if you deal with the static force, something like it just the offset of the response, and there's nothing change as compared to the free vibration. So we go for the harmonic excitation because this is the commonly force that induced to the system lah. So because it's related with the frequency of excitation, because we want to study about the resonant phenomena and so on lah. The effect of the frequency of excitation towards the vibration response. Okay, so this case we consider that the force is equivalent to F naught cos omega t. Okay, so this is the sinusoidal function. Okay, so F naught here is represent the magnitude of the force applied. Okay, so in the unit of Newton lah. So it's depend on the system. Okay, so this is the magnitude of the force. Higher force, of course, it can produce the higher displacement lah, because it's related to uh, the deflection lah. Okay, and then there is also function of omega here. Okay, so function omega here actually is represent the frequency of excitation, the speed of excitation, and which is refer to the same meanings. Okay, so which is the equation can be represent into this formula. So M is the mass of the system, the mass equivalence, and K equivalence, equivalent to F naught cos omega t. Okay, and then the transient solution, which is can be represented into this one. So this one is the same as last week lah. Okay, so cos and sine, which this one actually the same lah. The same. This one is equivalence, equivalence to A sine omega n t plus sine. Okay. So just represent to this formula. If you want to find A, which is square root of the C1 square plus C2 square. Okay. And then the psi is an inverse tangent for C1 over C2. And this one transient, which is the response is in the refer to the omega n, so which is natural frequency lah. Okay, so now we know that we consider that the motion also in the harmonics, so which is x equal to a sine omega t. Okay, so under this excitation, because we know that if we induce a 10 hertz, the response also should be 10 hertz. So that's the dynamics. Okay, and then x double prime actually can be represented as a minus omega square because after we differentiate, so we consider that x is equal to sine, so x dot equal to cos, and then we differentiate cos, we got minus sine so minus omega square omega square is come from the what we differentiate the inside sine function. Okay, so we got this relationship. Okay, and then the x actually, which is what we are tested, which is the response. So the response is equivalent to F over K minus M omega square. Okay, sine omega t. So sine omega t actually is referred to the harmonic response because the force is harmonic, the response also harmonic, which is the same frequency. Frequency doesn't change. Okay, the frequency is same. If you excite 10 hertz, the vibration also 10 hertz. If you excite, you change the speed 20 hertz, the response also should be 20 hertz. So that's the common sense. Okay, and now what we're interested is about the amplitude. What is the amplitude of vibration? Okay, so the amplitude of vibration is depend on this, all these three parameters. So F, K, and M omega square. Okay, so F is the force. Okay, and then the force applied, the magnitude of the force applied to the system. Higher force, higher amplitude, that for sure. Okay, and then there is a resistance to the force, which is come from the stiffness and the inertia. So which is can be equivalent to force over stiffness minus inertia. Okay, so if you got the lower value for this determinants, and then you got higher vibration. The higher determinants, we reduce the vibration. Okay, so for this case, stiffness is remains constant lah. Stiffness force, which is depend on the K lah. Okay, and then the inertia is depend on the speed of excitation lah. So speed of excitation, which is m omega square. Okay, so which is depend on the speed of excitation. You excite at different speed, the resistance from the inertia will be different. Okay, so that's what we are trying to look in for force vibration. Okay, so now we look at that the excitation. Okay, so the excitation F sine omega t. So we start with the omega at the from the low frequency to the higher frequency lah. Okay, at low frequency, which is the excitations close to zero lah, the frequency excitation close to zero, which is a very low excitation speed. Okay, so for this case, initial resistance is close to zero lah, because omega close to zero. For this instant, the displacement of this mass actually is depend on the stiffness lah. Okay, so which is equal to F over Kx lah. Sorry, X equal to F over K lah as sine omega t. Okay, so which is this one is a almost equivalent to the static condition lah. So because the frequency is too slow, the motion something like this lah, very slow motion. Okay, so which is the initial force doesn't have a significance value lah. Okay, so which is dominated by the stiffness. Okay, so this one is almost in static condition lah. So which is the displacement is depend on the amount of force and the stiffness for the system, and then the displacement x is in phase to the force lah. So in phase meaning that is the motion is same direction lah. So which is if this is the mass, if you push downward and then the mass also goes to downward direction. Okay, if you change direction of the force, which is upward, the mass also move in the upward directions. Okay, so that's the meanings of in phase. Okay, for low frequency to resonance frequency lah. Okay, so when we increase the speed, okay, we increase the speed of excitation. So which is keep increasing until it reach to the resonance frequency lah. Okay, so the stiffness resistance is constant. So which is it doesn't change to any value even you increase the speed, so it's remain constant. Okay, however, when you increase the speed of excitations, okay, so it will increase the initial resistance. Okay, so which is can represent into quadratic quadratic equation lah. So m omega square. Okay, so it keep increasing lah. Okay, so keep increasing. So when if we refer back to this equation, when this one increase, so which is the determinant's value will be reduced lah. So when it reduce, so meaning that x will be higher. Okay, so until it reach to the point that the inertial force have equivalence magnitude with the stiffness force, which is it will cancel out each other. Okay, so at this point, okay, so the amplitude increase lah. Okay, so the amplitude increase, because amplitude increase when the speed increase lah. So because due to less of resistance, but when it comes that when the omega m omega square is equivalent to k, so which is at this instant, there is no resistance. Okay, so as a result, the mass is without any resistance, so can go at any position lah. So because k minus m omega square is equivalent to 0, so which is f equal to 0 is equal to infinity, so which is there is no resistance at all, and it can be very high displacement lah. Okay, so that's theoretically lah. This condition actually um, we call as a resonance lah. So which is this instant is the speed at this point is equivalent to natural frequency or with the resonant frequency. So it's come from this relationship lah. So that's why we found that the omega n natural frequency is equivalent to square root k over m lah. So actually that is the resonant. Even you give a very small amount of force, but if you excite at the resonant frequency, the reaction or the response for the mass can goes up to infinity. Okay, that is why we should consider the resonant phenomena lah our design stage to avoid that condition. Okay, so it can be very high, the mass move without any resistance, so that's uh, but this one is for the spring the undamped system lah. So the undamped system, but in actual it cannot goes up to infinity lah, because as mentioned before, so any kind of the system must be it should have the damping elements lah. The damping elements, so which is the presence of the damping can control the vibration response lah. But again, the damping is not too significant lah. If you excite at the resonant frequency, it can you can reduce a certain amount, but the vibration will be very high. So that's why in industry, when your system is running at resonant frequency, then you face very high vibrations, and there is a highly potential to the system to be fail. So it's high likelihood to fail. They call of terms in the industry. Okay, so from this point to this point, you can see that it keep increasing because the resistance is keep reducing. So that's why in industry we not only consider the resonant frequency, but we must set the range, operating range lah. So normally it must be 20% away from the resonant frequency. Okay, so for example, if you found that because when the operating speed is close to the natural frequency, you still can get a high amplitude lah. So for example, if you found that the natural frequency at 10 hertz, the proposed running speed or operational speed should be around less than 8 or is greater than 12. That's the common practice. Okay, so this one is when it reach the resonance frequency. So this one we call as the resonance. So which is the system has totally lost the ability to resist. So which is there is no resistance at all. So this one is a natural frequency. So basically we can represent as omega naught lah, omega naught or omega n. Okay, then there is the condition which is after the resonance. Okay, so after resonance, if we keep increasing the speed, okay, so if the frequency is increased further, the inertia will overcome the stiffness. So which is for this case, the inertia has a greater magnitude, okay, as compared to the stiffness. So because it's already in this part lah, okay. But again, found that when m omega is greater than k, so mathematically you will got the negative sign lah, okay. So negative sign, okay, in motion, the negative sign actually represent the direction of the mass, okay. Okay, so the direction actually, if you refer, it goes, we call as a out of phase. So out of phase, 180-degree out of phase. So which is the mass move in the opposite direction of the force. Okay, so if the force in the upward direction, the mass will goes to the opposite, which is downward direction. And if a force downward, it goes to the vice versa lah. So that's the properties the dynamic properties. If you excite the operating speed is greater than natural frequency, okay. So that actually this one is happen so it been proved by experimental, by the slow motion camera. So after you keep increasing, and then it goes to the out of phase. And this one also used as an indicator to sense the resonance so which is based on the phase diagram lah. So if there is a phase shift, okay, so mean that in that area there is a resonance frequency, okay. So this happen after you increasing lah. And then if you keep increasing the speed, okay, so if you keep increasing the speed, and then um, which is the dominance resistance is come from the initial initial, when the initial is too high as compared to the stiffness. This one we can call as the mass control so the mass control, which is the motion is dominated by the mass, okay. So the system in the isolation, okay, so which is at this point even you give the higher force, but the amplitude will be very small that's why um, if for the single degree of freedom, if you use the very high speed, and then the vibration will be small, okay. So this one is due to the isolation so to isolate the system, you can increase the speed at very high speed, which is away from the resonance frequency. So that's the features the features for force vibration, okay. So which is the force vibration, you don't have to calculate the frequency, because the frequency is followed by the excitation frequency. You excite 10 hertz, you got 10 hertz. But what we are interested about is the amplitude, okay. How much the vibration response for the system and the force vibration, okay. So from that we can conclude. Oh, okay, should be like this okay. So this one, if you keep increasing, okay, and then after that it change out of phase, okay, so which is a force positive equals to negative, okay. And then the magnitude goes when goes to infinity, it close to zero lah. So which is if you use very high speed. Okay, back again to the you know excitation. So we based on this formula lah. Okay, so we know that for the particular response, okay, so particular XP, XP is refer to particular solution or particular response or steady state lah. Okay, so which is equivalence to X cos omega t. Okay, sine or cos doesn't matter, you can choose, you can use sine or cos lah, but for this case most of the book using cos because it's easier to find the solution lah, especially once you convert it to this form. Okay, but actually it still represent the same thing lah. Okay, so as mentioned before, omega is operating speed. Okay, so you don't have to calculate, but you have to calculate the operating speed lah. So it means you have to calculate based on the unit conversion lah, because sometimes it give you the unit of the hertz, and then you have to convert radian over seconds lah. Okay, so now what we're interested about is the amplitude of vibration. Okay, so X is a max amplitude, so which is can be derived as a F naught K minus M omega square. Okay, can be simplified into this form. But actually, I prefer you to use this solution because it's easier. So this one, sometimes you are confusing. So this one actually is referred to the static deflection. Okay, so the static deflection is not static deflection due to the mass, but static deflection due to the force applied. So force F basically is F over K. So F over K. So you we got this relationship lah. Okay, so which is the amplitude is depend on this equation. Okay, and then for the total response, okay, so total response for this system X ST, which is the particular solution, sorry, the homogeneous plus particular. Okay, so that's the general solution lah. Okay, so actually it's depend on the question. If the question asks you to find the steady state response, then just consider the steady state response. Okay, so but if the question asks to find the solution for the total response, so mean that you have to consider the total response. Okay, but the tips is if you are given the initial condition, which is there is an initial velocity and initial displacement in the question, so mean that you have to solve the total response. Okay, so to solve the total response, so mean that you have to solve everything here lah. Okay, so first you have to solve the particular. Okay, so particular solution is easier to solve lah. So because it's depend on the equation, just use this equation to find the amplitude, and then the frequency, you have to calculate the frequency lah. So that's the difference. So particular we use omega, homogeneous we use omega n, because homogeneous is depend on the natural frequency. It will oscillate based on the natural frequency. Okay, and then once you solve this part, and then you have to solve C1 and C2 lah. Okay, so C1 and C2. So omega n you have to calculate based on the stiffness and mass. Okay, so you have to consider the displacement equation and also the velocity equation. So which is you have to differentiate this equation. Okay, so differentiate this equation to get the velocity to get the velocity. Okay, so from that you have two equations with two unknown, and then I think it's not problem to find the solution. Okay, and this one actually the general solution. Actually you can use this system if you face a very simple system, which is straightforward system. Okay, but if you deal with the small complex system, I prefer you derive from this solution. Okay. So this one is a general equation. General equation. So if you're given the initial condition, initial displacement, and initial velocity, actually you can use this condition lah. Okay. But you have to consider that here K, M, okay, so must be K equivalence or mass equivalence. If you deal with the rotational motion, so rotational motions, for the rotational motions, the equation is almost same lah. Okay, so but you just have to change this one is a theta. Okay, and then F, you must use the moments, moment M naught. Okay, so K is a KT, M here is a J naught. So you have to consider the equivalence for all the parameters. Then you can use this equation. So to avoid confusing, it's better for you to derive from this solution. Okay. So maybe I will show to you later on the example and the solution. The max amplitude. So I think this one the same lah. To the x value. It's not x over static deflection. This equation you have to move to other side. Okay, so we go to the last part there. So this one actually part of the example. Actually, there is a lot of more force that can induce in the harmonic form. Okay, but one of the most popular option, which is considered as unbalanced force. Okay, so the unbalanced force when there is a rotating system and there is an unbalanced mass. So when it's rotated, it can produce the unbalanced force. So the harmonic force depend on the speed. Okay, and then the magnitude of here is equal to F naught. F naught if you refer to this equation. Okay, so F naught, which is the magnitude. Example for the unbalance. Okay, so unbalance, which is depend on the unbalanced mass. Okay, and then the distance from the unbalance, which is the center of gravity for the unbalanced mass to the center of rotation. Okay, so mass to, if you put any unbalanced mass, and then the distance as compared to the center of rotation, then times by the omega. So which is a higher speed produce a higher unbalanced force. So that's the example of for the rotating unbalanced force. Okay, so which is part of example for the how we can produce the harmonic type of force, and it's common. It's common. Even you go for the industry, when there is rotation, when there is a reciprocating motion, it can produce all this kind of force. Actually, it's a lot more. There is an unbalance. If the misalignment also can produce the harmonic kind of force. Even the defect to the system, it's like the gear defect, okay? The bearing defects. This one also can produce the harmonic force. So that's why in industry, if you face with high vibrations problems, so it's come from, can refer to this solution. High vibration, so high amplitude. High amplitude is dependent on this. Okay, so if there is a machine defects, so it produces a higher force. So F naught, high F naught, of course, is proportional to the amplitude of vibration. So this one, sometimes the high vibration is due to the machine defect. So you can off if you just repair the defect, change the components, and it's gonna move. They can reduce that one of the solution. If there is no problem with the F naught is still low, but you still get the high vibration response, then it might come from the resonant issue lah. So the resonant issue is based on this K, M, and omega lah. So you can solve based on this option. You can change the operating speed. Okay, so when you increase the operating speed, then you can keep it away from the resonant frequency. Then you can reduce the vibration. Or otherwise, if you cannot change the operating speed, sometimes when you go industry, when you use a motor sometimes there is no controller to control the speed of the motor, so you cannot change the speed, and then you can go for the other option. So which is you can change natural frequency. So natural frequency is depend on the stiffness and mass. Okay, so you can stiffen the structure, you add the spring elements, or you can put additional mass to control the natural frequency. But normally the option, most of the solution is stiffen the structure or loosen the structure, so which is control the stiffness for the structure. So that's the common practice to solve the high vibration issue in industry. So actually it's based on this formula. Okay, so X F naught K minus N omega. So that's all lah. So you solve F naught, or can you solve the dynamic properties, or you change the natural frequency for that system. Okay, so I think that's all. We already reached 10 o'clock. So have any question before we end our lecture session? Okay, if no question, I think we just stop here. Okay, see you again tomorrow.
Assalamualaikum doktor.
Yeah, yeah.
Can I confirm back the date for midterm exam?
Okay, midterm exam on week 6, Thursday at night.
Thursday at night, doktor.
Hmm.
Uh,
Okay, yeah,
okay,
8 to 10, 2 hours.
8 to 10. Okay, doktor.
Okay, is it clear? Okay, I will write the announcement lah on the kalam after this. Forgot about that.
Okay, doktor. Thank you.
Okay, thank you for your attention. See you again tomorrow class.
Thank you, Doktor.